So hi, thank you for coming. My name is Mario Fusco, and I'm here to speak about laziness in Java, which could be seen also a good continuation of what of the former Venkat's talk. Okay, Venkat mentioned laziness in his immutability talk, and now we can explore the advantages of laziness a bit more. So what is laziness? Normally, you are not used as a Java developer to think in lazy terms. Normally, when you pass a method when you pass an argument to a method, the argument is fully evaluated and then passed to the method. Okay. With laziness is happening something else. The argument is not fully evaluated until the method needs it, until the method has to use it. And hopefully the method will never have to use that argument, so you will never evaluate it. In Java, when you have strict function, everything is evaluated. All arguments are evaluated regardless they are useful or not. Okay? While with laziness, only what is needed will be actually evaluated. So to recap, strictness, which is the opposite of laziness in programming, strictness is about doing things regardless. Okay? While laziness is about nothing things to do and just doing those things, the really necessary thing. Okay, I said Java is a strict language. Everything is not lazy. This is mainly true. Of course, there are something that has to be lazy. Okay, so you have the Boolean shortcut operator. You have the ternary operator. You have the if-else condition, the for loops, and a notable addition to Java is the Java 8 streams, which, as Venkat said, take advantage of laziness. Okay, but the question is, can exist a totally strict language? I believe it cannot, because if the ternary operator, in this case, if you wouldn't have the shortcut end in Java, this statement will fail with a null pointer exception in case the person is null, because both part of the both predicate, the left and right predicate of the condition will be evaluated regardless if the first is true or false, and then you will get a null pointer exception on the second. So laziness in some cases is unavoidable. It's really, really hard, if not impossible, to think about a programming language which doesn't have some part of laziness in it. Okay, and moreover, if you think about it, we also used to act in a lazy way. We learn to be lazy very early when we grow up. If you know me, you know that I'm like to make example based on my parenting experience. And if you have kids, probably you have seen a scene like this. I tell to my daughter Sophia, is your room, is everything sorted out in your room? Did you put your toys away? And she says, yes, everything is fine. Okay, everything is fine. Okay, now I'm coming to check if it's true or no. And at that point, Sophia start putting stuff in the right place. Start ordering the room. Okay, so Sophia learned very early to be lazy. Because why? Because lazy is the most effective way of doing things. If I'm not going to check the room of Sophia. Sophia has wasted work reordering a room without any need, because I'm not going to check it, okay? So she learned very early to be lazy. And actually, it's quite simple to have lazy evaluation in Java 9, in Java 8 by means of lambda expression, okay? So here I was trying to recreate a ternary operator in with a function, okay? So instead of using the result one is evaluated using the ternary operator, while result 2 is evaluated doing calling this ternary method that I created there. Are the two things the same? Unfortunately, they aren't, because as I said, the ternary operator is lazy, while I'm passing val1 and val2 to the method, both val1 and val2 will be evaluated regardless which of them is used in the method or not, okay? But it's really simple in Java to turn this stuff into a lazy evaluated method, to recreate a ternary operator with this method. The trick is just modifying the two argument, changing the type of the two argument, and instead passing supplier to them, okay? So I'm not passing to the method the result of the invocation. I'm passing to the method two lambda that will eventually invoke val1 and val2 method, and I'm calling those supplier, the method, the lambda that will supply the value only if and when it's necessary. Okay, so I'm not calling both the first and the second. I'm just calling one of them. And you can see this technique that already used in many libraries around. For instance, log4j is using it. If you before Java 8, what you did, if you have a log sentence that was really computation intensive, you wanted to avoid it when you are not doing tracing. Okay, if you have a trace logging, you want to, of course, calculate and print the string, but otherwise you don't. Okay, so to avoid the wasteful computation of the string, you just put it inside in this if block. With Java 8, you don't need this anymore. You can do this. Okay, you don't need to put the if block. You won't pass the string, but you will pass a supplier of that string, and that supplier will be called by log4j if and only if it is in tracing mode for that specific method, for that specific class. Is that okay? It's clear? Okay. So to cut it short, laziness is the ultimate optimization technique, performance optimization technique, okay? Why? Because there isn't anything more efficient than not doing something at all, okay? You can do something very, very fast, but probably what you're doing very, very fast is not useful at all. So why are you doing it? The most efficient thing is not doing it at all, right? So, and as I said, Java 8 Stream, it's a very specific case because for the very first time, we had in Java an API which is lazy. What does it mean? Laziness allows me to have an infinite stream. Why? Because the stream is not computed when it is created. Otherwise, it won't work, of course. You couldn't have an infinite stream, which is not lazy, of course. And moreover, when you call this map and filter method, when you call all the intermediate method, as I said, these methods are acting as my daughter Sophia. Do the map, okay, I'm done. Do the filter, okay, I'm done. And in reality, it's not doing anything, okay? Because you are not asking for a result. You haven't gone to check the room of Sophia yet, okay? At the moment you go to check the result, at the moment you ask for a result, at the moment you do a terminal operation, which is defined first in the case, all the other operations are triggered in a lazy way, and then you have the advantages that also Venkat showed in his talk. Okay? So a stream is not, this is a very common mistake. A stream is not a data structure per se, okay? A stream eventually wraps a data structure, but what a stream is a lazy specification of how to manipulate that data structure that is wrapped by the stream, okay? So, and of course, there are things that you can do much more elegantly if you use laziness. So let's suppose that we have a list of the positive integers, and we want to filter only the prime number, and we want to take only the first end result, okay? And the algorithm explain it in a declarative way, in a functional way, is exactly as I said, okay? And why I could implement this algorithm in this way, in this declarative way, because I'm leveraging laziness. If I wasn't leveraging laziness, of course I could obtain the same result, but I will have a list of imperative steps which will be harder to read and harder to implement, okay? So, of course it's doable, but what a mess. So, and why laziness also allow me to achieve this result? Because laziness allow me to also better clarify the concern of each statement. It is enabler for a separation of concern. And let me show this with a very simple example. Okay, so what I'm doing here. Here I have a log file, okay, and I'm filtering only the line that starts with error. I want to filter only the error statement in the log file, and I want to take the first 40 of them. Okay, can you spot it? Yeah. Let's try to write this using a stream in a declarative way, in a functional way. You can do something like this, okay? And okay, I don't want you to focus on the fact that this second version is more compact, is more concise than the former one, okay? Of course, yes, this is true. It is true that it's more readable, but there is one more important concept here, which is the separation of concern. In the stream-based implementation, we have one line dealing with the opening and traversal of the file, while this concept is spread around in the imperative implementation, and the same apply for the filter, the same apply for the limit. Here I want to limit this thing to the first 40 statement. I'm just saying limit 40 in one case. I'm having 3 statements in the second case that are spread around my code, okay? And same thing for collecting the result into a list. So you see, in the declarative way, you have step by step a clear separation of concept of what each statement does. Okay, so cool. Cool. Now we know streams are great. Let's try to also use stream for the prime number problem that I presented you before. Okay, so just to recap, I have an infinite stream of prime number, of a positive number. I want to filter the prime number, and I want to take only the first 10. Okay, so yes, I could do this way. Okay, I have a method that returns a Boolean saying if a number is prime or not, and then I can use this predicate, this method, to filter the numbers, and then I can limit the result to the first 10, and I'm done. Okay, So yes, this works, but to be honest, this is a bit inefficient. Why it is inefficient? Because every time I'm deciding if a number is prime or not, I'm not using all the primes that I computed before. If I'm deciding if 7 is prime or not, I'm also dividing it by, I'm dividing it by 3, okay, but I'm also dividing it by 4. And I don't need to divide it by 4 because I already know that 4 is not a prime number. So it's pointless to do this. It's a waste. Okay, so I would like to keep track of the prime number that I have already found during the search, and just reuse the prime number and divide the new candidate number only for the prime number that I discovered so far. So how could I do this? Okay, this is, I tried to write this in Java, and yes, it looks cool. In pseudocode, it makes sense, but of course, this doesn't work, okay? Why this doesn't work? So what I'm doing here, I'm recursively calling primes, okay? And I have a method that that takes, in one case, the head of the stream, the first item of the stream, and in the other case, the tail. And I'm reusing the head of the stream, which is the first prime that I found, to filter the remaining part of the stream. And I'm doing this recursively. You see, primes recalling itself. So this could work, sort of, but there are two reasons why it is not working. The first reason is that by calling this head and tail, I'm actually calling two terminal operations on the same Java streams, which it isn't allowed. Once you have called a terminal operation on a stream, you are done. You cannot call another operation on it, otherwise you will get an exception. And the second part, which is even more relevant for my example, is that you don't have lazy evaluation. So this recursive call of primes will just blow up the stack without doing anything useful, okay? And this is not because my original idea was wrong. It's just because this is how Java works. Meaning that if I try to implement exactly the same idea in Scala, it works. Okay, because Scala is this fancy concatenation operator, this dash colon colon, which does what I was saying before. Okay, it does a concatenation, but in a lazy way. So if you run this stuff in Scala, it works. It's exactly the translation of what I did before in Java. In Java, you can do that. In Scala, you can, because Scala has this. It's a more a functional language, so it has more this concept of laziness embedded in the language. Okay, so but this is doesn't mean that we cannot achieve the same result in Java. So let's try to create a different data structure that is lazier than the stream. Okay, it is a list. Okay, it is a list. You can think about this as a stream of number, but what is but I can implement this in a very lazy way. Okay, so the interface is that I have an head. This list is made by an head, which is the first element, and a tail, which is the remaining part of the element. I have an operator that say if the list is empty or not, and I have a way to filter the list. Okay, really simple. But where is the added value? I can implement this interface in a lazy way. Okay, so if you look about it. In the implementation of this interface, I don't have the tail. I have a supplier of the tail, okay? Here I'm introducing the laziness. So this list is made by the first element, which is the only element that I have really already calculated at that point, and the tail is made by the tail hasn't been calculated yet. I just have a sublayer of the tail. So when you call tail, you will be returned with another lazy list, which is the remaining part of the list where only the first item has been calculated. Okay, and with this data structure, you can implement a lazy filter, which is like that. Okay, which is okay. If the list is empty, I return the list, and then I have I test the predicate on the head of the list, and if the predicate is true, I return a lazy list with the head and the filter recursively called on the tail. Otherwise, I directly recursively call filter on the tail. And why can I do this? Because it is lazy, okay? Because of the laziness, because the tail is just a supplier, okay? Once I've done this, I can finally implement in exactly the same idea that didn't work in Java but worked in Scala. This is exactly the same, the translation of the Scala code, but with this new data structure that I've implemented in Java. So how can I use this? Okay, I started with a list that infinite list that start from 2. You can see better how it works here. I start with a list that has just 2 as the head, and the tail is a supplier of all the numbers starting from 3, right? And then I call give me the primes. Filter this list with only the primes, and the result will be the 2, because 2 is a prime, and then the test will be true. And then I have a supplier of the primes from 3 of the list of items starting from 3, filtered by 2. Okay, because if you remember, filter called himself but in a lazy way. And then I say, give me your tail, and the tail is from 3 filtered by 2. So it's the list starting with 3, and having as tail a supplier of from 4 filtered by 2 and filtered by 3. So you see what I'm doing? I'm concatenating in a lazy way the filtering of only the prime number. Okay, and once again, if I ask again, give me the tail. Now the head of the list will be 5, and the tail will be the supplier of all the prime number starting from a given point, which is the point that I haven't calculated yet, filtered by only the prime number that I've found so far. So this is how it works internally. Question? Okay, maybe give a look at the code after the talk, and hopefully it will be clear, or it is already, I hope. Okay, so one more thing. There are a few ways to traverse a list. Normally, you can do this in an iterative way, but a more functional style is the recursive way, okay? And in reality, about iteration, you have 2 kinds of iteration. You have the external iteration, which is the iteration we are used to use till Java 7, which is, let's say, a for loop that iterates a set of number, okay? And then with stream, we introduce this internal iteration, okay? But as I said, there's this internal iteration made with stream. But as I said, there's a third way. The third way to do this is not iterating, but recursing, okay? So this small method that sum all the number from 0 to n you see, recursively call themselves. So recursion is very elegant, and in many cases, it's the preferred functional way of doing things. And there are many algorithms that relies on recursion. Okay, for instance, I supposed to have a string, and I want to test if this string is a palindrome or not. Okay, if you can read the string in the same way from left to right or from right to left. Okay, so what I do here, I start with the string. I remove the spaces if there are, and then I take the very first and very last character, which are not spaces. I compare them. If they are different, I know that the string is not a palindrome and I return false. Otherwise, I remove the first and the last character and I call is palindrome recursively. Okay? And if I end up with an empty string, I know that the original string was a palindrome. Very simple. What's the problem with this? Venkat mentioned this problem in his talk. I mean, if you have a deeply recursive algorithm, what you can expect at some point that, yeah, it works in simple cases, but if it is deeply recursive, you are adding call on the stack and ending, and at some point you will end up with a Stack Overflow error. So, I have this filtering predicate here, okay, and if I try to run this, everything is fine, okay. But if I try to apply the same algorithm with a very long string, which, by the way, it is a palindrome. I don't know what this thing says, but apparently it's valid English, and I found this on the internet, and it's a palindrome. If you try to also check this string with the algorithm I mentioned it before, you will get, of course, a Stack Overflow. Okay. So because it is calling this palindrome too many times, and at some point you blow up the stack. Okay. Normally you have 6,000 calls available on your stack, and after that you will get a Stack Overflow exception. Okay. So what you can do to fix this? I mean, I don't want to give up to this algorithm. I want to use the same algorithm, but avoiding this problem. In reality, in Scala, you don't have this problem at all, because there is something that is called tail call optimization, meaning that if a method is returning the result of the very last call, as in this example, that last call is not added to the stack. Okay, so this is the bytecode, pseudo bytecode that you have in Java. If you do the same in Scala, the invocation of do that is not added to the stack. The control is directly passed to do that, because that is the value that I'm returning. Okay, this is called tail call optimization. The last call is optimized, is not the old function is popped from the stack before adding the new one. Okay. So my algorithm in Java would work, by the way. Okay. In Scala, this is exactly the same algorithm in Scala, and this work without any problem. What we can do in Java? We can do something to also have to work around this problem, and they have tail recursion also in Java, which with a pattern that is called Trampolines. What this pattern does, when I invoke a function, with this pattern, I'm not returned with the result, because if I need to return the actual result and the result is calculated in a recursive way, you will end up with the Stack Overflow problem. So when I call apply to a function, I'm not returned with the result, but I'm returned with another function. Okay, and then I call on it apply again and again and again. Okay, at some point I will be returned with a function which is the last one, the terminal one, and at that point I can call apply on it and get the result. Okay, how can you implement this stuff in Java? I declared this interface, which is a tail call, which is a supplier of a tail call, meaning that when you call get on it, you will return another tail call. So the function returns another function when it is invoked. Okay? So this is an intermediate tail call, so it's complete return false. You cannot ask the result to it, you will get an exception. But when you invoke it, you will call this linearized stream of function one after the other, as I showed in the former slide, until you get the result. So there is a terminal variant of this tail call, which return true on the is complete, and only on this you can call result. Okay, and here I have a static factory method that is called done, which return a terminal tail call. Okay, so if you see what I do on the invoke method, I'm lazily iterating this potentially infinite list of function until I find one which is complete, which will be the terminal tail call, and on that one I can say give me the result. Okay, is this clear? So you can have this new class in your code if you want, and then it's quite straightforward to write it, but it's much more straightforward to use it. Okay, so how can I fix my problem? As I said, here the problem is that I'm returning a Boolean. Okay, what I want to return really is a lazy supplier of this Boolean, is a tail call of the Boolean. Okay, so in this case, I got the empty string by removing all the character till I get the empty string. So I'm done with a value 2, with a result true. So I just say this. Okay? That is this done method that I mentioned it before, which create the terminal call. Okay? And the same thing if I find two different characters. In this case, I'm done with false. Okay. And the other thing is that when I do the tail recursion, I cannot do the tail recursion this way. I need to return a supplier of the tail recursion. So it's as simple as doing this. Okay? That's all. And then here, this is palindrome method is returning a tail call. I just say invoke on this, and I'm done. Okay? So if I try to rerun my former example, you will see that it will calculate the is palindrome function even with a very, very long string. So it is clear why this works. It is not adding up on the stack the function. It is linearizing them. Okay? This is how it works. Very simple. Okay. Okay. One last example. I know we use a lot dependency injection. We really use a lot. I really use a lot. I often find that I abuse of it. And there is something, well, using dependency injection is very nice, but in my opinion, there is something not really sounding in it, okay? Because, okay, of course, it is eager in nature, but there are worse things. The problem is that you can, in general, you cannot use the new keyword. The main problem is that the beans, your pojos, your object, are not, the life cycle of those objects are no longer under your control. Okay? The life cycle of the object are under the control of the dependency injection framework. So there is this thing that I called all your beans belong to us syndrome. Okay? You lose the control of the life cycle of your beans because everything is under the control of the dependency injection framework. Okay? And this life cycle could become quite complicated. And depending of the scope of this object, you could have a thread problem, you could have concurrency problem. I find that it's really, everything is great until it works, but it's really hard to debug when it doesn't work from some reason. Okay? And as I say, it's something that is really easy to abuse, and sometimes also it breaks encapsulation. So don't get me wrong, dependency injection is great, but I believe we are abusing of it, and there could be a different way of doing this. Okay, and in reality, the annotation-based dependency injection transforms a compile time problem into a runtime problem. Okay, in this case, I believe that dependency injection is sort of transforming Java into JavaScript, in the sense that if you have a problem, you probably would like to have that problem at compile time, but instead you will have it at runtime because you have a missing injection. Okay, so how can we achieve a similar result in a more functional way, in a lazy way? Okay, here I'm introducing the reader monad. The reader monad, it's a monad, okay? What's the particular thing of this monad? Normally, in a monad, you wrap a value, and the monad gives you the map and flat map method to compose with itself. So the optional monad wraps a single value. The stream monad wraps a list, eventually infinite list of values. The completable future wraps a value that is no longer, is eventually not yet there. It will be computed sometimes in future. Okay. What the reader monad does is something that you use for laziness, because it doesn't wrap a value, it wraps a function, as you see. Okay, so it's used for laziness and for function composition. Okay, so what the reader monad does is making lazy computation explicit in your type system while adding the logic to apply and compose it. So let's come with a very simple example. I have this bean, which is a bank account, and I can do some operation on this bean. I can open the bank account and I can credit some value on it, or I can debit money. Okay. And what I want to do every time one of these operations is performed is log in it. Okay. And normally what I do is that, in my case, this logger is very simple. It's just a consumer of a string. It's something that consumes a string. So it's something that could consume a string and print out on the standard output, or print out on a file, or send by email, whatever you want. And this logger usually is injected. Okay, so I'm injecting this implementation of the logger, and everything works, hopefully. So if you use dependency injection, as I said, you cannot use the new keyword anymore. If you do this, you are creating an account without a logger, and the things that happens is that you will get a null pointer exception as soon as you try to use it because you don't have any logger injected in it. Okay? So let's try to achieve something similar with this reader monad. Okay? So as I said, I have this account. I created it in this way. I try to perform some operation on this account, but if I try to do so, I will get a null pointer exception because there is no logger injected. Okay? So what I want to do, I want to inject the logger in a lazy way. I want to inject the logger only when this is necessary. I want to possibly define all the operation that I want to perform on this account without really performing it. Okay, this is similar to the stream if you think about it. And only when I trigger all this computation, I will inject the logger through the reader monad or through a simple function, as we will see after. Okay, so how can I do this? Okay, as I said, you can think a reader monad is just a wrapper of a function. So in some way you can think about it just as a function. Okay, so I'm writing reader here of logger and account, and in this moment you can think about this as a function from logger to account. It's the same thing. Okay, what I will do is this. I will lift my account, my object A, inside the reader monad, okay? And I will lift this with the object itself and a B consumer. A B consumer of the object, which is the account in my case, and the dependency that has to be injected, which is the logger in my case, okay? So when I use this lift, I will be returned with this account, with this reader of logger and account. So I'm lifting the account. And as I said, I need to pass this B consumer. I need to pass a function that when it is invoked, it injects the logger into the account, which is simply account set logger, nothing else. Right? Okay. Okay. And at this point, I can perform my operation. So I can perform. I can open the account for Alice. Okay. And then I can perform all this other operation. The only thing I have to do is place them into a map, okay? Because I want to do them in a lazy way, okay? And as you see, okay, as you see, I haven't any logger so far. I performed the operation. Actually, I haven't performed them. I defined them, and I haven't used any logger so far. Now, I can trigger the operation, and to trigger them, yes, I will need to pass a logger. So I can say apply on this reader monad. As I said, you can think about the reader monad as a function. So I can call apply on it, and I just pass to it a logger, which is in my case is very simple. It's just the console output. Okay. And yes, and then I'm done. So if I try to run this, It works. And it is logging the operation, okay? So what's the main point here? Is that dependency injection is eager. It has to be performed when the object is created, so at the very beginning of the life cycle of that object. And this is often not necessary, okay? What this new way of doing things allow you is to clearly separate the business logic definition from its execution. So I have a business logic definition when I don't need any dependency to be injected, because I'm not performing action, I'm just defining them, okay? And only when I go to execute the operation, I will need actually my dependencies to be injected, okay? And in reality, so this is a scheme of what I'm doing here. I have an account, I'm lifting this account into a reader monad, I'm calling map, and again, and so only when I'm ready, I can apply this function with the dependency and be returned with the value, okay? And in reality, I used this abstraction, but if you think about it, what I'm doing is just function composition, okay? So in reality, for this very simple case, I don't need to introduce the reader monad at all. A simple function will be enough. So let's try this. I have a function that is doing exactly the same thing that I'm doing here. You see, it's taking an account and injecting a logger inside it, okay? And I call this function inject. And then I can define a function that goes from a logger to an account. I'll call it f, which is this inject function, okay? And then on this inject function, I can compose this injection function with all the operation that I want to perform on the account. So I can do exactly the same thing that I did here. With only one difference. The method is not called map, as you know, but it's called and then. Okay, so I'm composing the function this way. Oops. Okay. And then I call apply exactly in the same way. And for this simple use case, I will obtain exactly the same result. So I don't need that reader monad at all in this simple case. Why I'm using that reader monad? Because the reader monad allow me to give me an higher order abstraction for composition of function. Okay, so let's suppose that I have a second object which is a money transfer. So when I call transfer on an account, I will be returned with a money transfer, and also the money transfer needs a logger to work exactly in the same way as the account did. In this case, I won't be able to use the simple function anymore, but I can fix the problem by using the flat map instead of the map, okay? So when the transfer method return me the money transfer object, I'm also lifting it with its injector of the log there, okay? And in this case, of course, I cannot call map, I will call flat map because I'm passing to it not a function from A to B, but a function from A to a reader of B, right? And in this case, I will get for free the injection of the logger on both objects, okay? And it will work as you expect. So the key takeaways is Java is a strict language, but with lambdas, you can make it lazy. With a supplier, you can make it lazy in a very simple way. And again, laziness is the most important form of performance efficiency, because there is nothing more efficient than not doing something at all. And laziness favors declarative programming, is an important part of functional programming, and favors and allows separation of concept. Some algorithm can be implemented in a more elegant way by using the functional approach, and the functional approach very often requires the laziness. And in some simple cases, the one I showed you, you can probably try to avoid the traditional dependency injection and use a simpler approach based on function injection, as I showed you. And I'm done. Is there time for question or no? Okay. One. Is there a question there? No. Okay. So ping me offline if you have question, and thank you.